Welcome back. So let's try this again. We have this model here with k users and empty transmit antennas. And now we could design this W in different ways, but one obvious way would be the following. We set W equal to H Hermitian and then H Hermitian inverse. And in order to check that this expression is meaningful, we want that this matrix here is a small matrix, so of size k by k. Otherwise, it's not invertible. Okay, so this here is k by mt. This guy is mt by k. So the whole thing is k by k. And this is a small matrix. So this means we could not, for instance, write H Hermitian H inverse. This does not exist because this would be a matrix that is of size mt by mt and it can be at most rank k. So this is not allowed. Anyway, so let's suppose we say W is equal to this. What do we have then? Y is equal to HWS plus noise is equal to H. All right, plugin was W, H Hermitian, H Hermitian inverse S plus noise. Then these cancel out, so then I find that Y is S plus noise. And then this means that what receiver K sees will be its data symbol, SK plus noise NK. So this means no multi-user interference. And again, this here is the multi-user interference. Now, it is possible that I cannot evaluate this inverse, right? Because even though this is a small matrix, still maybe it could be bad, poorly conditioned if all the users are, for instance, close to each other. And what you can then do is you can select the best k users among the set of users that you have. So let's suppose that there are 10 users in your system. You could select the best 5, and for the best 5, write this equation and find W, and then send only data to those best 5 users. And this is called user scheduling. So you would first send to the first 5 users and then to the next 5 users, and you go in between them. It is also possible to do pre-coding with statistical channel state information, so when you only need the distribution of the channel, not the channel itself. Now, this may seem very nice. There is one problem here, that we need to make sure that we don't send with too much transmit power. So this W affects the transmit power. A way to see this is that if the channel is poorly conditioned, this inverse will explode and then you will use too much transmit power. So we need to make sure that we don't use too much transmit power, and this will be done in the next slide. So the scenario is as before, k users with one antenna, one base station with m antennas, and then the channel will be a k by m channel. So this is the downlink channel. We've seen zero forcing precoding where we set W equal to this, so the H Hermitian times the inverse of H Hermitian, but this may lead to too much transmit power. So we want to make sure that this precoding does not lead to too much power. So we want to enforce that the precoder by itself, in terms of its norm, this is called the Frobenius norm of this matrix, which is the trace of W Hermitian W, is equal to the total transmit power. And this we do in order to ensure that the total transmit power is constant. One way to do this is to scale, for instance, the whole precoding matrix with a constant. So we will set W equal to a constant times H Hermitian, H Hermitian inverse. And then we can choose this constant alpha, to make sure that this is met. So this will work, but this will lead to probably equal SNR for all of the users. You can check this. So this will have Y equal to alpha S plus N. So that means that for each user, YK is equal to the same alpha SK plus NK. This means that the SNR for user K will be alpha squared ES over N naught. So all the users have the same SNR. Maybe you don't want that. You can actually do something better by adjusting the power as follows. So by choosing W to be H Hermitian times a scaling matrix here, where you put powers on the diagonal. Okay, so you say that W is H Hermitian inverse times a diagonal matrix, which we here call dp1/2, where dp is equal to p1 till pk, where pk is the power for user k, with now then this constraint here. So we need to then make sure that we can now choose the powers here along this diagonal to make sure that the constraint is met. So we choose this thing to make sure that the total power is fixed. And this then leads to a kind of optimization problem where we maximize over these power allocations some cost function, and this could be, for instance, the rate, for instance, sum k log 2 1 plus pk es over n naught. But it can be another objective function too, it's up to you, subject to the total power constraint. So we make sure that this is satisfied, and this is given by this expression. And when we do that, what will happen at user k? Y will be H Hermitian inverse dp to the 1/2 times S plus noise. Okay, where, oh, that's not a very good color. This, of course, is W. And then I can again cancel most parts. So this will give me dp 1/2 S plus N. And then this implies that for user K, it will see Yk, which is square root Pk times Sk plus Nk. And this means that the SNR rho K for user K is Pk times Es over N naught. And then this is exactly what I optimized here in this rate equation. So this is one way to do pre-coding for the case where each user has one antenna. And you can generalize this to the cases where users have many antennas, but then the math becomes much more involved. And I don't want to go into details about this. A question that I write here is, why does singular value decomposition not work? Right, so why can you not just say, okay, H is U sigma V Hermitian, and then I apply standard singular value decomposition. So I have my data S, I do V, then I have X, I send it over the channel, I do U Hermitian, I get Y tilde. Why does this not work? Think about this. The reason that this does not work is because to do the combining, so the pre-coding you can do. Pre-coding is fine, this is okay. The problem is that the combining you cannot do, because the combining would require that the users together do this. The users together would take all their observations together and multiply with U Hermitian. So the answer then is that now I forget which matrix it was, but it U Hermitian of the observations is not possible, because it requires inter-user collaboration. So that's why we cannot use SVD in this context. All right, so now you've seen a little bit about multi-user MIMO. In the last topic for today, we will talk about massive MIMO. And as you can imagine, massive MIMO means just more antennas. So why do we want to talk about massive MIMO? The reason is that in multi-user MIMO, even though in theory this works well, putting many antennas at the user device, such as a phone, may be very costly. And then the gains are still relatively limited. Even though we have this linear scaling of capacity, for instance, we need many antennas to see this. So when the base station has only 10 antennas, there's no real benefit of this. Also, the signal processing can be very complex, both at the base station and at the user side. We've seen that when each user needs to recover multiple data streams, the complexity grows exponentially in terms of the number of data streams. Massive MIMO makes things massive in one dimension and very simple in the other dimension. So the simple dimension is the user dimension. For each user, you just give one antenna, while the base station you give lots and lots of antennas. And this picture shows the difference between current 4G systems, which is multi-user, well, which is you could see as multi-user MIMO, and here we have massive MIMO on the right. So here you have a base station with a few antennas, a user with also a few antennas. You have multiple users of this. In 5G, you will have a base station with a lot of antennas, hundreds of antennas, and each user has a single antenna. In 4G, by sending signals, you will cover multiple users, and you will then do pre-coding to help the users recover their data. In 5G, because you have these lots of antennas, you can create basically dedicated spatial streams per user with very limited processing, even when each user only has a single antenna. Now, to make things a bit more difficult, I changed the notation. So I will use by M the number of base station antennas and by K the number of users. But we still use the number of transmit and receive antennas, so NT and R. In the uplink, when you go from users transmitting to the base station receiving, the total number of transmit antennas is equal to the number of users. The total number of receive antennas is then the total number of base station antennas, M. And here M is much larger than K. So hundreds of antennas and maybe 10 users. In the downlink, the number of transmit antennas is M, right? Because the base station is sending in the downlink. The number of receive antennas is K, the total number of channels seen, the total number of receivers that you have, the total number of users. Here, what I'm showing is in the uplink, base station with M antennas, very large, K users, so only 4 users here. And each user has its own channel in the uplink. This channel is a column vector, so it's a long vector, which we can decompose as a path loss component. This is path loss plus shadowing. And then the remaining part is the small scale fading. And then, of course, each of the users will have its own channel, but this is the channel for user H, for user I. And this is the uplink channel. Now, in massive MIMO, you can create favorable propagation conditions which allow for linear scaling of the capacity. And there are two scenarios here. The first one is non-line of sight, and I think then, okay, we'll first focus on the non-line of sight case. Later we will talk about line of sight. But let's take a quick break now, and then we come back.